Hey guys, so here is the video for our ratios of similarity notes. We've talked a lot about similar figures last semester. We've spent a lot of time finding missing sides of similar figures, so now we're going to go a little deeper into it and think about like, okay, well, if the sides of similar figures are proportional, in what way do the areas change, and what way do the perimeters change, and that kind of thing. So let's do a little experiment here. So if we look at this little flag and this big flag, and we kind of ask ourselves, okay, well, how much bigger is this flag than this one? And in particular, how much bigger is this width than this width? So just eyeballing it, I would probably say it's like double the size. So what we can go ahead and do is trace this, and let's go ahead and test that theory. So we'll put one here and see if we can fit another one. And sure enough, we can very perfectly fit two of these right in there. So that tells me that that big base, or that big width, is in fact double or twice the size of the little one. So that tells me that if the side is double the size of this one, then that is in fact the side ratio, or the zoom factor, between the corresponding sides. All right, so that's dealing with the sides. Now let's think about how many little flags, entire little flags, could we literally fit inside of the big one. So I'm going to go ahead and trace this guy to the best of my ability. This one, that's not so bad. Probably my best yet. So let's go ahead and see how many of these we can fit. Now in class I had you guys guess. You already know the answer to this, but fine. Okay, so that's one so far. Here's another one. That's two. There's still some space here, so let's get a third one. Third one looks like it could fit there pretty nicely, and there's in fact still a little bit of space left right here in the middle. So let's put one more and flip that around, and that one fits quite nicely in this middle gap. So as we can see, there are actually 4 of these flags in this big one. Now you might have initially thought that because this flag is twice as big as this one, that we would fit twice as many triangles. So we would fit 2 of these, but clearly it's much more than that. So that being said, we can go ahead and put the 4 here. There's 4 flags. The area, as you take a shape and make it bigger or smaller, does not change by the same zoom factor that the sides change by. So for some notes here, if we are working with sides and lengths, then it does change by the zoom factor, right? We know that if you are given 2 shapes and the side length on one and you're looking for the other, you would just do the side times your zoom factor, which we're going to call zoom factor R here. Okay, and that's pretty basic. We've been doing that for quite a bit. That's old news. If we were working with perimeter, meaning if I knew that the perimeter of this flag was like 10, then what would the perimeter be of this one? And in fact, the perimeter also changes by the same zoom factor as the sides. So if the zoom factor is 2 and the perimeter here was 10, this one would be double, so 20. So here I would put the original perimeter times R. No different. All right, and area is when it does in fact get a little bit different. If I gave you the area of a shape, and then I made that shape bigger and I gave you a second one, then we don't multiply the old area by the same zoom factor anymore. In this one, we ended up multiplying by 4, not by 2. And the reason that we multiplied by 4 was because 4 is 2 squared. So area actually changes by the zoom factor squared, not just the zoom factor. All right, so that is really the heart of this topic here. So let's do a quick demo. Here are two pretty random shapes. The side of this shape right here is 7 feet, and the matching side on the other bigger shape is 21. To get from 7 to 21, we had to multiply by 3. Okay. And that tells me that the zoom factor is 3. And another word for zoom factor that we're going to be using more is linear scale factor. Okay, that's another word for zoom factor, and I really want you guys to start getting comfortable with the linear scale factor terminology. All right, so then the area, on the other hand, to get from 40 to 360, in fact, did not multiply by 3 like the sides did. Instead, it multiplied by 9. 40 times 9 is how we would get to 360. And the reason that it's 9 is because 9 came from 3 squared. And 3 was the zoom factor. So just like we just talked about in the notes here, to get from the original area to the new area, you multiply by the zoom factor squared, and that's exactly what happened here, right? 40 times 3 squared would get us this 360. All right, so let's do a couple practice problems. We have Kelly with this weird, funky little cowboy hat looking shape. And she's telling us that the zoom factor here is 5. So we have an R value of 5. And she also told us that the area of her little shape is 17 square millimeters. So if the area of the little one is 17 square millimeters and the zoom factor is 5, then the area ratio, or the area scale factor, would then be 5 squared. So 25. All right, so this was the linear scale factor. Linear scale factor. Whereas this one is what we would call an area scale factor. Scale factor is what we multiply by to figure out the information for a similar figure. So if I'm trying to figure out the missing side on a bigger shape, I would use the linear scale factor. If I was trying to find the missing area of a bigger or smaller shape, I would use the area scale factor. So then, to actually find the new area, we would take the 17 and we would multiply it by that area scale factor, which is 25. All right, that would give us an answer of 425 millimeters squared. All right, on to the next. All right, we have some similar hexagons, one's bigger than the other. We know that the area of the little one is 263.1, and we don't know the area of the bigger one. That's what we want to find. What we do know is that one of the sides on the small one is 10, and the matching side on the bigger one is 30. So now the first thing we're going to want to do here is to figure out what the zoom factor is. Okay, when in doubt, find a zoom factor. So I can actually do that by taking a look at those matching sides and saying, okay, well, what's the scale factor here? How did I get from 10 to 30? Hopefully you would realize that I multiplied by 3 to get there. And if you didn't realize that, no worries, you can always do a little division, because sometimes the numbers won't be nearly as simple as 30 and 10. And you would get 3. Okay, so this is my R, aka my linear scale factor. Also, zoom factor. All right, so now we can go ahead and use this R to help us find the new area. So knowing that that is our zoom factor or linear scale factor, we can say, well, if I want to find the big area, let's take the little area, the one that we know, and multiply it by something. Now, our regular linear scale factor is 3. So if I want the area scale factor, we need to multiply it by 3 squared. All right, so what we end up doing is 263.1 times 9. That 9 is the area scale factor. All right, so that's just something you would type in your calculator, and hopefully you would get the answer 2,367.9 square units, and then you're done. All right. One more problem here. We have these two similar rectangles. We know that the perimeter of this left one is 30 inches, and we don't know the perimeter of this one. That's what we are looking for. So now, just like the last problem, the first thing we want to do is figure out what's the zoom factor here. How did we get from 5 to 10 with these matching sides? So you would do 10 divided by 5, and you would get 2. This is my R, which is my linear scale factor, also known as my zoom factor. And I can use that to figure out my new perimeter. Now I know the old one is 30. Now remember, we're not working with area anymore. This is perimeter. And if we refer back to our notes, perimeter changes just by R, just like how the sides do. It's not fancy like area is. So we would actually use that same exact zoom factor to figure out the new perimeter. So we would find that our big perimeter is 60 inches. All right, and this 2 is what we plugged in here. All right, go ahead and give the open math problems a try. Good luck.